I, Dr. Alok Kumar Gupta, welcome you in the video program of Physics. For this program, today our expert is Sri Sher Singh, Principal, Navig School, New Delhi. Dear learners, in the previous program, we have already discussed about wave optics and its application. That is, what is wave, wavefront, how they form and other related phenomena like refraction of light, interference of light, diffraction of light, etc. So, continuity of that, today we are going to discuss about resolving power of telescope and production of polarized light. So, for this program, I welcome Sri Singh sir, please.
Thank you, Alok Gupta. Today we have selected the phenomena related to light existing in nature, and definitely you will enjoy that. As in previous program we have discussed that wave is a periodic disturbance carrying energy from one place to another. Regarding the nature of light, several theories came in existence. One such important theory is Huygens and Fresnel's ether wave theory. So, on the basis of this theory, today we are going to discuss the very important function of the telescope, that is its resolving power. You must know that it is the ability to form distinctly separated images of two objects which subtend a very small angle at the objective. It is a reciprocal of the limit of resolution theta of the telescope, where theta is the angle subtended at the objective by the 2 point objects which are just resolved. Just resolved means which can be seen just separately when seen through a telescope. Smaller the value of theta, larger the resolving power. So, we can say that resolving power is 1.22 lambda divided by d, where d is the diameter of the objective and lambda is the wavelength of light used, and here 1.22 is the correction factor. So, the resolving power of telescope depends on the diameter of the objective. Larger the diameter, greater is the resolving power.
Since our eye is also an optical instrument, so what about its resolving power?
Oh, very good question. When we talk about the resolving power of the eye, it is the ability of the eye to form distinctly separate images of two distinct objects. The minimum angle which is a human eye can resolve is given by 1.22 lambda divided by d. Here d is the diameter of the pupil. If we take wavelength of light 500 nanometer and small d about 2 nanometer, then it can be seen that this theta comes equal to approximately 1 minute. So, the resolving power of eye is about 1 minute, and eye therefore cannot resolve two objects if they subtend an angle smaller than 1 minute at the eye. It is because of this reason that we are not able to see two headlights of a car separately when the car is far away. Now, we can also connect it to the normal magnification of the telescope. Because of large diameter of the objective, the limiting theta angle for just resolution for a telescope may be as low as 1 minute, but we will unable to see the image of the two stars separately because of resolution limit for our eyes is about 1 minute. And we can also say that this 1/22 divided by this resolving limit is equal to magnification multiplied by the limit of resolution and its reciprocal, as we can calculate it as beta is equal to m alpha, where beta is the limiting angle of the eye, and it can be simplified as m is equal to capital D divided by d, where capital D is the diameter of the objective and small d is the diameter of the pupil. It is a very important relation.
So, how can we understand about the nature of light?
Oh, to understand the nature of light, we must know that light is an electromagnetic wave, it is transversal in nature, and to have feeling that it is transversal in nature, we should learn or understand the phenomena of polarization. during polarization of light, the particle of the medium do not vibrate. Light waves are not mechanical wave. It have been proved that theoretically and experimentally that light is an electromagnetic wave. In electromagnetic wave, electric and magnetic field which are at right angles to each other, they vibrate perpendicular to the direction of propagation of the light. So, an electromagnetic wave is travelling along x axis, the electric field E vibrate along y axis, and a light in which electric field vector E vibrates only along a single direction perpendicular to the direction of propagation. This is called linearly polarized wave or polarized light. Such a wave is also called plane polarized light or plane polarized wave, because the angle wave is contained, the entire wave is contained in one plane. A linearly polarized wave is usually represented by a double arrow indicating the two equal and opposite directions of maximum electric field E. The electromagnetic wave emitted by an antenna is also linearly polarized light. The light can be used in the direction of the propagation of electric field. This is because an ordinary source of light contains enormous number of atoms and molecules, and these are oriented in a medium, and consequently the light given out by such a source in a given direction contains of independent wave trains whose electric vector E through perpendicular to the direction of propagation of light are normally oriented in the yz plane. We can summarize light by an ordinary source consists of broken chains of wave trains whose vibrating electric vector through right angles to the direction of propagation are not necessarily parallel to each other, but are randomly oriented in a plane perpendicular to the direction of propagation of light. Such light is called an unpolarized light. And one more thing, you can see in the diagram, the light is shown by the double arrow in all the directions, and you can see these are the vibrations of electric field parallel to the axis of propagation. We can see single arrow and double headed arrow are the vibrations which are perpendicular to the direction of propagation. So, any vibration in an unpolarized light can be decomposed into two components which are mutually perpendicular. For example, the vibrations shown in the figure can be resolved into two components, only along y direction and the other along z direction. An unpolarized beam of light is therefore represented as shown in this diagram. Here the polarization is taking place, unpolarized light is coming and it is going in two directions, and these two directions are mutually perpendicular direction. And when I say mutually perpendicular direction, one is reflected ray and one is refracted ray, and there is a very beautiful law which we call Brewster's law. It was discovered by Brewster that light reflected from a medium of refractive index n is completely polarized if it is incident at an angle IP such that tangent of IP is equal to n. The above statement is known as Brewster's law, and the polarized beam by the above method has vibrations perpendicular to the plane of incidence. When light is incident at the polarizing angle IP, the reflected light is linearly polarized. Now, from this law we can say that the refractive index is tangent of IP, which can be written as sin IP upon cos IP, and we can also involve here the Snell's law, which is sin IP upon sin R is equal to refractive index, and we can have a beautiful relation IP plus R is equal to 90 degree, means reflected and refracted ray are complementary.
So, how the intensity of light varies during polarization, sir?
When you talk about the intensity of light, we have to consider the Malus law, and this law states that the intensity of polarized light is maximum intensity of the light falling on the polarizer and square of the cosine of the theta, where theta is the angle between polarizer and analyzer. And here it is very important to know that the electric field vector of incident light and the polarizing direction, the characteristics direction of transmission of the analyzer should be understood to understand the propagation of light with intensity. So, Morley's law can be proved as, let A be the amplitude of the linearly plane polarized light incident on the analyzer and theta the angle between the electric vector of the incident light and the characteristics direction of the transmission of the analyzer. The amplitude A can be resolved into two components, as we have already discussed. These two components are A sin theta and A cos theta, and plane of polarizer you can see in the diagram. So, now A cos theta, which being parallel to the characteristic direction of the analyzer, gets transmitted, and A sin theta, which being perpendicular to it, gets absorbed. So, the intensity of light emerging out of the analyzer is therefore given by I naught is equal to k A cos theta square, where k is the constant of proportionality, and it can be also written as I m is equal to cos square theta. In this case, we can say the Morley's law does not hold in the above if the incident light is partially polarized. This law is valid for complete polarization. When the incident light is unpolarized, then sin theta can be taken all possible values. We have to put average value of cos square theta, which is half. Hence, an ideal analyzer transmits 50% of the unpolarized incident light. Now, we can talk some other phenomena related to the nature of light. The color of sky is blue, and how it becomes blue when we say that sunlight consists of all the 7 colors, where 6 colors are lost. This color of sky is totally dependent upon a phenomenon known as scattering of light, and the intensity of scattering of light is directly proportional to negative fourth power of wavelength of light, or you can say that inversely proportional to the fourth power of wavelength of light. What happens when light passes through the atmosphere? The heterogeneous particle of the atmosphere, like dust particle, air molecules, etc., scatters the light, and in scattering the intensity of short wavelength is scattered more, and intensity of longer wavelength is scattered less. So, when light passes through the atmosphere, we see that in our visible spectrum blue light has very short wavelength, and violet also has short wavelength, but our eyes are not so sensitive for that. So, the scattering light intensity is more of blue light, that is why sky appears blue.
Can you explain the color of sky?
Before explaining the color of sky, here we can have a very small activity. This is a very small activity. You can see that when this laser light is thrown on a paper, it does not appear in between paper and laser torch. You cannot see light anywhere else, just it is leaving the spot on the paper. But when we are creating atmospheric effect by producing some smoke, and smoke particles here act as the heterogeneous particle present in the atmosphere, you can see how this light is scattering. Now, you can see in the smoke scattering of the green light. So, now you can understand how the sky is blue. Here this is the scene of blue sky. Now, it can be explained, you consider that this is the atmosphere and sun is very near to the horizon, and when sun is overhead, mostly we have all the colors of light are reaching, but at the time of sunset and sunrise this phenomena occurs differently.
As you explained, sir, sky is blue, but sun appears red at the time of sunrise and sunset. Why?
Yes, yes, we can explain with the help of this slide is because at the time of sunrise the light is travelling from longer atmosphere to the earth. So, the blue light is scattered into the sky and the light which is reaching to the eye of the observer is of red color. That is why at the time of sunrise the sun appears red, and same phenomena happens in case of sunset also. Here you can see the sunrise scene where the atmosphere of the sun or its surrounding of the sun appears red, and at the same phenomena you can see at the time of sunset. So, how this color of the sun at the morning and at the evening or at the time of setting are different and make the environment very beautiful. This is also depends upon the scattering. So, now it is very much clear the color of sun at the time of setting and rising.
What about, sir, color of cloud?
Oh, very beautiful question. Now, you can see the clouds, the color of the clouds is white, but why it is white? It is very important to know, and this is the eagerness of every learner. Large particles do not show the select scattering as is being shown by the small particles. Clouds being a collection of large dust particles and big drops scatter light of almost all the wavelength equally. Therefore, the mixture of all the colors of light makes the clouds white.
Sir, you explained sky is blue and sun appears red at the time of sunrise and sunset also, and also you explained clouds are white. Then what about the color of rainbow and how they form?
Oh, rainbow is very beautiful phenomena. So many literature is available on the beauty of the rainbow. Here you can see the rainbow in the sky. Just after the rain, very small drops of water remain suspended in air, and they act as a very small prism, tiny prism you can say.
Okay.
So, when light passes through this tiny prism, dispersion of light takes place, and in dispersion of light, light splits into its constituent colors, that is 7 colors, which is the basic formation of the rainbow which you can see in the sky. Another thing, these are the small drops and this is the observer, and observer back is towards the sun and the sun rays are falling on these suspended drops, and you can see these drops are dispersing light at different angles as coming from the sun. So, two types of rainbow are formed. The lowermost rainbow is primary rainbow and the uppermost is secondary rainbow, but secondary is not always appearing with the primary. Sometimes it appears, sometimes does not appear, but when there is a formation of single rainbow in the sky, it will be only the primary rainbow, or if two rainbow are together, then it is the secondary rainbow. So, this is how the natural phenomena of light existing in nature and in our surroundings.
So, learners, I think after seeing this beautiful talk, you will be more clear about wave optics and its application like polarization of light, resolving power of telescope, etc., and so many beautiful phenomena available in the nature due to light. So, for this fruitful discussion, I thanks to Sri Sher Singh sir who came here with his valuable time and spare with us. Thanks sir. Thank you again.
Thank you.